Let's see, is microphone on? Yep, it's on. Hey, so, welcome back. So this video is just going to be sort of a bonus video on top of the differential equations class I'm doing. So there's this whole realm of special types of derivatives, and and of these, time fractional derivatives are fairly important. The reason why I want to mention them is because one of the ways you can define them is through the Laplace transform and using convolutions. And so this gives us a nice little exercise to see how you can do some more interesting type of work beyond just regular differential equations and initial value problems. So what I'm going to do is I'm going to introduce you to what are called the Riemann Label and Caputo Fractional Derivatives. Now, you might ask, what is a fractional derivative? And the short answer is it's like taking half a derivative, or like a quarter of a derivative, or a pith derivative if you want. Something that's not an integer number of derivatives. So, and the basic idea is that you should be able to take, say, two half derivatives and you get a full derivative out of it. So there were, this sort of work initiated, well, questions about this work initiated back in the 1600s or so, and there was a letter between, I can't remember, it was between Leibniz and another famous mathematician, where the other mathematician asked Leibniz, what do you think it would mean if instead of, in your notation, d by dx, we put d to the 1/2 dx to 1/2. And Leibniz said, I don't know, but it'd be very interesting to find out. Now, some people actually say that this is how research in fractional order systems actually started, but realistically, if somebody's just asking a question that doesn't have anything really substantial to follow it up with, you don't say that they actually started the research. Real work in this started with Abel and Riemann-Liouville back in the 1800s, and this is where you start to get something that's like what we call the Riemann-Liouville Fractional Integral, which is really what enables all of the definitions of fractional calculus that we're going to talk about today. But in order to do that, we're going to take a few steps to introduce it. So first of all, I know you've probably seen the gamma function back in Calculus 2 if you had a decent professor, and if you didn't, nothing against your professor, who knows, they had other priorities. But basically what we're going to have to do is we're going to have to introduce the gamma function, which is sort of a fractional analog of the factorial. And then on top of that, we're also going to have to introduce this sort of anti-differentiation formula called the Cauchy's formula for iterated integrals. And so this is actually kind of a cool thing where basically if you want to talk about the nth antiderivative of f, well, you can take, say, in a whole bunch of definite integrals from 0 to t over and over again, and then you can basically write out what the nth antiderivative for a function is using integrals. And then what you can do is you can make a few exchanges of variables inside of integrals, and that actually gives you what is going to become actually a convolution. And so then we can see that we can perform a large number of integrals with just by convolving with the right function, and that function is going to be basically t to the n. And once we do that, that allows us to talk about what happens when you take a fractional integral, and that's going to really come down to, instead of taking t to the n, we're going to have, say, t to the r or t to the q. I like q better. We'll take t to the q, where q is just any real number. And once we have a nice Cauchy form, the nice Cauchy iterated integral formula, it naturally changes to a fractional analog. And then we can see that this actually is given by a convolution. And because it's given by a convolution, once we know the gamma function, we can actually go ahead and take the Laplace transform of it. And then we have a whole new way of solving a special type of integral differential equations, which are called fractional order differential equations. And there's two different ones. There's a Caputo fractional derivative where you take differentiation first and then you do a fractional integral. And then there's a Riemann-Liouville one where you take the fractional integral and then you take integer order differentiation. Each of these largely agree with each other except on the initial conditions. And it turns out that the Caputo derivative works a lot better as far as initial value problems go because it has integer order derivatives, or initial values. So you can relate it to position, velocity, acceleration, etc. Whereas Riemann-Liouville ones are actually based in fractional order initial values, which are a lot harder to define. And that brings up the larger problem of what do all these mean? Well, so for regular derivatives, we have, this is your velocity, and second derivative is your acceleration. It's not as clear-cut with fractional derivatives, but what we can say is that in some modeling problems they actually end up working better, and they come up a lot in what are called viscoelastic systems, and that's where they got sort of more of their popularity back in the 1970s and 1980s, and then they've sort of built up into a whole research domain all the way up to today. So say the past 20 years have seen a huge amount of development where you have everybody trying to convert everything to a fractional order system one way or the other. Some of them are really kind of crap papers where they just, for no reason at all, put in a fractional order, and then it's meaningless. It has no connection to anything that anybody cares about. But then you have other nicer papers where basically they take where they base it on some problem they're actually trying to resolve, and those are a lot more interesting. And so the success of the fractional derivatives makes me really kind of want to place this in sort of an extra bonus thing in my future classes, just so people have a vague idea of what these things are. Even Richard Feynman I mentioned fractional derivatives at some point, and so it's it's not completely unheard of a topic. Anyway, so we'll jump into it, and this should be fun.
Okay, so let's get started. All right, so we're going to be talking about fractional calculus, and the idea is that we're going to be taking, say, 1/2 derivatives in some fashion, but we need to be able to define what the heck that means. So in order to do that, we're going to need a couple of formulas. First of all, we're going to include something called the gamma function. This you might have seen from Calculus 2 if you had an ambitious Calculus 2 professor, or just one that really liked indefinite integrals. We're also going to need Cauchy's formula for iterated integrals, and this is going to require a little bit of Calc 3 know-how, mainly just exchanging multiple integrals. But the idea is that you're just basically trying to take higher and higher antiderivatives of a function, and you want to be able to write that in a nice closed form. We also have the Riemann-Liouville Fractional Integral, and that's going to use, it's going to basically be a direct generalization of Cauchy's formula from integer number of, say, 1, 2 antiderivatives to, say, a 1/2 antiderivative, or a pi antiderivative, or whatnot. Then we're going to use that in combination with integer derivatives in order to make what we call the fractional derivatives, Riemann-Liouville and Caputo fractional derivatives specifically. There's actually a whole slew of these things, but only a handful have really been seriously studied. And then if we have time, I'll talk about some initial value problems with them. All right, so to start off, let's talk about the easiest bit. This is the gamma function. So the gamma function is sort of an interpolation of the factorial, so where you actually have gamma n plus 1 is equal to n factorial. And the idea is that with n factorial, for instance, we know we can write this as n times n minus 1 factorial. The gamma function works pretty similar. The idea is that this is not just any interpolation where basically, say, we have the factorial at integer points, so say 1, 2, 3, and this would be at 1, 2, 6, and at 0 is also 1. If this was just a straight linear interpolation, we'd have something like this. But we'd lose all the nice properties that we have from factorials. So Euler decided to make a generalization and he made one that respects this. So basically for all z, and we write z because this is complex, we can use complex variables. And so, and basically the idea is this: we have this nice identity where the gamma function satisfies this, and if, in fact, if we add in that gamma of 1 is equal to 1, then this uniquely defines the gamma function, just these two relations. And so this is really how you get a nice generalization to all real numbers or all complex numbers of the factorial. It isn't actually all complex numbers, but say all complex numbers where the real part of z is bigger than 0. Okay, so let's go ahead and just prove this property real quick, and then we'll move on. So basically what we have is we have gamma of z plus 1 is equal to the integral from 0 to infinity of t to the z minus 1 e to the minus t dt. Okay, so with that, if I just take u is equal to, sorry, that should be z plus 1 minus 1, because we're putting z plus 1 here. Now if I make u is equal to t to the z, then I get du is equal to z t to the z minus 1. And then I'm going to have dv is equal to e to the minus t dt, and that tells me that v is equal to e to the minus t. And so then I get t to the z, and I have e to the minus t, evaluating at 0 and infinity, minus the integral from 0 to infinity of t to the z minus 1 times e to the minus t dz. And then we're popping out a z as well because that was here. Okay, well, looking at this piece, remember this is really kind of being taken as a limit, so this is some capital N that's being taken as n goes to infinity. At 0, t here is going to make it 0 because we're saying that the real part is z is bigger than 0, or for if it's just real, then we're saying that z is bigger than 0, right? And so what we have then is that this is going to be 0, 0, and as we go to infinity, e to the minus t goes to 0. So that gives us that. And so what we're left with, and I forgot to flip a sign. There's a minus sign here, so that should go there. All right, so then what that leaves me then is just z integral from 0 to infinity, t to the z minus 1, e to the minus t dt, and that is exactly our definition of gamma z. Right, so we're done. Okay, barring those silly little mistakes I made in the middle, that's how you do it. And so now we have demonstrated that we now have a nice sort of interpolation of all the etc. You can demonstrate that z of 1 is equal to 1. That's just a simple integral of just e to the minus t. Okay, so let's go to next. All right, so now here let's talk about Cauchy's formula. Cauchy's iterated integral formula. So we know, for instance, if I want to take the antiderivative of a function, then I can say integral from 0 to t of f of tau d tau is an antiderivative of f, right? But now we'd like to find, say, a second antiderivative. And so, so for instance, then I can write integral from 0 to t, integral of 0 to, say, tau of f of, say, let's say tau 1 here, and we'll put tau 2 on the inside, d tau 2, d tau 1. Okay, now I'd like to be able to write this as, say, a single integral. And we can actually do that if we go ahead and exchange the order of integrals, and let's see how you do that. So if I fixed, say, tau 1, for instance, so making this tau 1, this tau 2, tau 1 always starts as, tau 2 for this tau 1, which goes from 0 to t, tau 2 is going to go from 0 to tau 1. So what we end up seeing is that we have this line, tau 1 is equal to tau 2, and we're going to go from 0 to tau 1 for tau 2, right? So basically this is how the integral is going right now. we move forward and we fix the tau 1, and then once tau 1 is fixed, tau 2 goes from 0 to tau 1. All right, but we'd like to do this in the other direction. I want to now swap the integrals, so now that means that we're going to fix tau 2, and then tau 1 is going to run. So tau 2, in this case, looks like if we want to cover the same area, tau 2 needs to start at tau 1, and it needs to go up to t. And tau 2 starts at t1, goes up to t, etc. Right? Okay, so now we see that the integral from that tau 2 is going to range from 0 to t, right? And the inside still stays the same as tau 2, but now we have d tau 1, d tau 2. Tau 1 is going to be going from, say, tau 2 all the way up to t. So let's go to tau 2 to t. And now we have tau 2 is running from 0 to t because it stops here. And so now we can go ahead and integrate it, because notice that the integrand here for the inside depends on t2, but the variable is t1 that we're integrating with respect to. So I can just go ahead and pull it out, and I can integrate it just like a constant, and that's going to give me t minus tau 2 times f of tau 2 d tau 2. That's not so bad. And if I want to clean up a little bit more, I can now just get rid of tau 2 because there's only one variable on the inside. And there we go. This is the first iterated integral. So if I want to integrate f twice, I just need to multiply by this first and just integrate once. It's a really nice handy tool. Now let's take a look at if I want to do it 3 times. And after we do it this one, a general pattern is going to end up emerging. So let's talk about it. So we go integral from 0 to t, integral from 0 to tau 1, integral from 0 to tau 2 of f of tau 3, d tau 3, d tau 2, d tau 1. All right, so you noticed on the inside here, these first 2 integrals are exactly the same as what we end up having above. Why is this not working? Oh my god. Alright, now we have to awkwardly wait for me to charge my pen. Okay, so now let's see. So what we can do then is we can go ahead and apply the above formula we just did. So instead of t though, we're going to have tau 1, and so that's going to give us the integral from 0 to t, or tau 1, of tau 1 minus tau something, f of tau something d tau something d tau 1. What is that something? Well, we noticed it has to match whatever was inside of f. What's inside of f is tau 3, so I'm going to put a 3 here, and there we go. And 3 here. Okay, great. Now we're back to this thing again, and this is the equation we get. Now I'm going to go ahead and swap the integrals again, and when I do that, this is what I get. I get the integral from 0 to t, integral of tau 3 to tau to t rather, of tau 1 minus tau 3, f of tau 3, d tau 1, d tau 3. Now here we actually have a term that depends on tau 1. But it's just a polynomial, and since f is still constant with respect to tau 1, that can still be pulled out. So we get the integral from 0 to t. It becomes tau 1 minus tau 3 over 2 squared, evaluated at tau 1 equals tau 3, and tau 1 equals t. F of tau 3, d tau 3, and finally, I get the integral from 0 to t of, when I put t in there, t goes here. That's good. When I put tau 3 in here, this becomes 0. So what do I get? I get t minus tau 3 squared divided by 2 times f of tau 3 times d tau 3. Or I get 1 over 2 factorial integral from 0 to t of t minus tau squared f of tau d tau. So if I want to do two antiderivatives, I just need this formula. And you can extrapolate and say, if I want, say, n antiderivatives, of f, or the nth antiderivative of f, that is going to be given to me by 1 over n factorial integral from 0 to t of t minus tau to the n times f of tau d tau. That's not quite true. So if I wanted 3 antiderivatives, which is what we had here, I needed to have a square on the inside. Here, so then I need n plus 1 here, or sorry, n minus 1, and 1 over n minus 1 factorial. And that's what I get. And so this is Cauchy's integral. Cauchy's formula for iterated integrals. Cauchy's integral formula is a different thing for complex analysis. Anyway, yeah. So, and now this will lead us into the Riemann-Liouville fractional integrals. Okay, so let's take a look at the iterated integral real fast. And okay, so let's take a look at the iterated. Okay, so now what we can do with Cauchy's iterated integral is we can actually come up with a Laplace transform for antiderivatives. Now this is actually one of the exercises in the Laplace transforms chapter for Nagel, Zaff, and Snyder, but it actually isn't too bad to do it after we have this and we know what the convolution is. So let's go ahead and write Cauchy's integral formula again, and so that is going to be the integral from, say, 0 to t of t minus tau to the n minus 1 times f of tau d tau, and this is divided by n factorial. All right, so this is Cauchy's integral formula, and what this gives us is, say, if we want, we can call this, say, the d by dt to the negative n of f of t, some people call it this. So this would be the antiderivative, so differentiating backwards. So what we can do is we can actually take a Laplace transform of this guy. So d minus n over d to the t minus n of f of t is equal to the Laplace transform of 1 over n factorial times this integral, 0 to t of t minus tau n minus 1 f of tau d tau. Right? Now, we can obviously take the constant factor out, but something you notice is that this is actually a convolution. So I can write this as, say, 1 over n factorial times Laplace transform of t to the n minus 1 convolved with f. And so this gives me 1 over n factorial times Laplace transform of t to the n minus 1 times the Laplace transform of f. And ultimately, we get 1 over n factorial times Well, the Laplace transform of t to the n minus 1 is going to be, it's going to be n minus 1 factorial divided by s to the n. This times the Laplace transform of f of s. And so what do we get? Well, we get, it's something striking me kind of weird. So 1 over n times 1 over s to the n, Laplace transform of f at s. Did I do all that right? I miscopied. This wasn't n factorial. This should have been n minus 1 factorial. This is what happens when you record over multiple days. Alright, so there's n minus 1 factorial and n minus 1 factorial and n minus 1 factorial and dead. This is gone. Okay, so that's what we got. So if you remember back from the chapter, and if you gave that exercise a try, it takes a bit in order to get to this form. But once we actually know the nice convolution expression for this antiderivative, we can actually very quickly, just exploiting the convolution property of Laplace transform, where it splits the convolution into two products, we can actually jump at this guy immediately. So now we'd have a new identity, where this guy is equal to this guy. I mean, that's really nice. Okay, so now why don't we talk about what a fractional derivative is? So we just talked about this guy being sort of a convolution as giving us antiderivatives. Now we're going to introduce what is called the Riemann-Liouville. Oops, I always do that. It's R-I-E. Riemann-Liouville Fractional Derivative. Or Fractional Integral. Let's start there. Okay, so what is this? So usually we just call this, instead of the negative, instead of using notation like this, we're just going to call this an integral operator, and we're just going to call this j. So j to the q of f at t. And what is this? Well, this is 1 over, let's pretend instead of q, I just have n. So we're going to have n minus 1 factorial integral from 0 to infinity of t minus tau to the n minus 1 times f of tau d tau, right? We just wrote all this. And so this would be the nth antiderivative of f. And so that's what I'm calling jn. And so mathematicians usually put colon equals if we're defining something. Okay, now our goal is to make this work for any real number, or at least any positive real number. And this is a spot where we might have some issues. But we just talked about changing this guy for a gamma function. So instead of n minus 1 factorial, I can write gamma n. And then actually that's enough. And so after gamma n, I can say, okay, well, what if I put positive q there? So I get gamuts of q. And I put a q here, and I put a q here. And then you can ask, well, what happens then? Well, that's what we call the fractional integral. And we'll say of order q bigger than 0. Okay, so now we can integrate fractionally. So for instance, I could put q as 1/2. I can say q is equal to 1/2, and that'll give me something. And yeah, so that's really nice. And we can see if I take the Laplace transform of j to the q of f of t, then this is going to be 1 over gamma q times the Laplace transform of t to the q minus 1 convolved with f. So then we get gamma q there times the Laplace transform of t to the q minus 1 times the Laplace transform of f at s. And so now you can ask, well, what is the Laplace transform of q minus 1, t to the q minus 1? Well, let's take a look. So t to the q minus 1. Now we kind of know what it is if I was to just have an integer. But let's see what we get otherwise. So this is going to be the integral from 0 to infinity of t to the q minus 1 times e to the minus st dt. All right, so my ultimate goal here is actually to change this whole thing to look like the gamma function. And that'll help me more than anything. So if you remember, let's go back a few slides. The gamma function looked like this. It's like a Laplace transform, except we don't have a minus st, we just have a minus t. So what I'm going to do is I'm going to come in here, I'm going to make a u substitution. I'm going to say u is equal to st. And that's going to give me du is equal to s dt, and that tells me that du over s is equal to dt. All right, more than that, I know that u over s is equal to t. So now I can go ahead and plug everything in. So now I get the integral from 0 to infinity, and now we have u over s in here, q minus 1. Then we have e to the minus u, and then we have du over s. All right, so now we're going to have a whole bunch of things popping out, and ultimately we get 1 over s to the q. S is constant with respect to u, so we can pull it out. And now we have the integral from 0 to infinity of now u to the q minus 1 times e to the minus u du. And what do you know? That is exactly the gamma function at q. So we get 1 over s to the q times gamma at q. So if I take this guy, call it star, and let's put this guy away over here, then star is going to be equal to, we're going to have the gamma of q is going to cancel with gamma of q, and we're going to be left with 1 over s to the q times the Laplace transform of f at s. And so that's really interesting. So if I wanted an integer order antiderivative, or at least the Laplace transform of the integer order antiderivative, then that would just be an s to the 1. If I wanted the second antiderivative, that would be an s to the 2, and etc., etc. So now if I want a 1/2 antiderivative, then I just put 1/2 in here. And that's really, really interesting, and it works really well. Okay, so what this tells us is that this fractional integral actually satisfies what we would expect to come out of a regular integral if we think of it in terms of the Laplace transform. Okay, so now let's talk about fractional derivatives. This is what we set out to do. So there's going to be two different ways we can take a look at the fractional derivatives. So fractional derivatives 1, and we'll say fractional derivatives 2. All right, so what is the first way to get fractional derivatives? So what we're going to do is we can fractionally integrate. So we have fractional integrals, and we have integer differentiation. Let's say that we want to have derivative of 1/2. And so if we think of this as sort of like f is sort of being at 0, and we can think of the antiderivative of f being up here and the full differentiation here at -1, we're basically trying to get to this point here. We're trying to get to, say, 1/2. Now, how am I going to do that? So there's two ways I can go about this. I can go ahead and start at f, and first I can integrate up to, say, 1/2. And then afterwards, I can start here, I can do one full differentiation. Gets me down to here. Right? And so this takes me to -1/2. Right? And so that's one approach to this. And so this is going to be, say, the derivative, the 1/2 derivative of f is going to be d by dt hitting on top of a fractional integral of 1/2 of applied to f of t. So this means that we're doing the fractional integral first, and then we're differentiating. Okay, So, and so if we want to do this more generally, then basically what we're going to do is we're going to go for a derivative of order, say, q bigger than 0. We're going to have this. So we're going to have the derivative of q, and we're going to say that q is between m and m minus 1, where m is an integer. So, so then we're going to apply the qth derivative to f, and so this needs to have a certain number of differentiation and a certain number of integrations, and apply to f. All right. So what I'm going to do then is I'm going to differentiate m times, and then I'm going to come up m minus q. Yep. So that should give me what I want. Just thinking real quick. So basically, we are going to be taking m minus q, and we're going to subtract m, and that's going to give me minus q altogether. And yeah, so good. So we want. We think of derivatives being sort of, quote, negative in this spectrum of differentiation and integration. Okay, yeah, so this. And this is called the Riemann-Liouville Fractional Derivative. All right. This was studied by, say, Abel and Riemann and Liouville back in the 1800s. It wasn't until later that another fractional integral came about, and this one ended up being a lot more applicable to to engineering applications or physical applications. And so here we're going to swap it around. So we're going to have integer order differentiation followed by fractional integration. Okay, so on this whole spectrum, if we wish, so where we have the integral from, say, 0 to t of f, which is the antiderivative, f prime, and just f, and we think this is, say, -1, 1, and 0, our goal is to get to the same spot. So we would like to get to, say, here. Call it 1/2. All right. So what we're going to do is first, we're going to take one full derivative. And then after that, we're going to integrate up here. Right? And so, and this is what's going to give us our fractional derivative of Caputo type. So what does this mean? So I'm going to say d star to distinguish it. 1/2 of f of t is equal to j to the 1/2 of f prime of t. And that is Caputo derivative. So first we take different derivative, and then we integrate it fractionally. Okay. So what do we get then? Let's see. So if I want so we say the Caputo fractional derivative of order, say, q with m minus 1 less than q less than m is given as, say, dq star of f of t is equal to j to the m minus q times dm by dt m of f of t. And there you go. So that's the Caputo derivative, and this came about in roughly like 1950s or 1960s. I can't remember right at the moment, and it was initiated by Caputo and other people. there's actually a really interesting way we can see that there's actually a difference between them. And so what this means is that these two operators actually don't commute, or rather you can't just willy-nilly apply one then the other. And we can see that through the Laplace transform. So let's take a look at the Laplace transform of f, of say the Riemann-Liouville derivative dq of f of t. All right, what do we get? So I get the Laplace transform of dq of f, and this is going to be the Laplace transform of the derivative with respect to, say, t. And let's just keep q between 0 and 1, so we only have to worry about one derivative on the outside. You'll get the idea as we go. So this is applied to j to the 1 minus q of f of t, right? Now, what happens? Well, to start off, we know what to do with derivatives. That's going to turn into a shift of our, a multiplication of by s of our Laplace transform. So we get this, s times the Laplace transform of 1 minus q of f minus the initial value of f, the initial value of the fractional integral of f, and where that fractional integral is 1 minus q. So, and then I can go ahead and wrap it up. We already talked about what this guy is, so it's going to be s times 1 over 1 s to the 1 minus q of f of s minus j to the 1 minus q f of 0. Okay, there we go. And then finally, this is going to be s to the q of f of s minus j to the 1 minus q at f of 0. Okay, so this is a nice handy formula. What we see is that when we take a fractional derivative of f with respect to Riemann-Liouville type, then what we get is s to the q. Where if I take a full derivative, I just get s to the 1. So again, this is sort of feeding into our intuition about how derivatives should work. And but then we end up having this. This is an initial value of a fractional integral of f. And that's really kind of confusing. There's really no good explanations of what these should be physically. There's a couple of papers out there that talk about a couple of physical interpretations. But on the whole, this is called the initialization problem for fractional integrals of Riemann-Liouville type. And now let me show you why people like the Caputo fractional derivative better for physical applications. So let's take a look at the Laplace transform of, say, d star q of f of t. All right, so it's going to be mostly the same game, except the order is different. So we have Laplace transform of the Caputo fractional derivative of order q acting on f. And so now let's split this into its operators. So it's going to be j to the 1 minus q times d by dt of f. And so right away, we can go ahead and apply our formula here. So it's going to give me 1 over s to the 1 minus q times the Laplace transform of d by dt of f. Okay, now let's go ahead and compute this. This is actually just straight from our table. So this is going to be 1 over s to the 1 minus q of f of s times s minus little f of 0. And so then, ultimately, what do I get? Well, I get s to q times f of s, just like what we got up here, minus s to the 1 minus q, minus f of 0 divided by s to the 1 minus q. All right, now I don't know about you, but that's a lot nicer than what we saw here. Sure, we still have this lingering s to the 1 minus q there, and that's not maybe the prettiest thing in the world, but at the very least, I can tell you what f of 0 is. If we're talking about a physical system, that is often just your initial position. And if we go on and we talk about higher order fractional derivatives, we need other integer order initial values, say initial position, initial velocity, initial acceleration, initial jerk, etc., etc., etc. And so it makes these, it makes the initialization of the Caputo fractional derivatives a lot easier to justify and a lot easier to work with. But yeah, so, and what that really drives home is that exchanging the order of these operators actually gives you something different each time. And now let's take a look at another example that will help us realize this. So let's just take a look at the simplest thing we can take a fractional derivative of. And so we're going to take a look, again, restricting q between 0 and 1, we're going to take a look at the Caputo fractional derivative of the constant function 1. Right? So what is this? Well, this is going to be j to the 1 minus q times d by dt of 1. Well, d by dt of 1 is 0. And so then we're left with j to the 1 minus q of 0. And what do we get? Well, if we want to go ahead and write out is 1 over gamma. So q 1 minus q to the, times the integral from 0 to t of t minus tau of minus q times 0 d tau. So it doesn't matter what this guy is doing, it's always 0. So this is 0. So the fractional derivative of a constant function is 0. Now let's take a look at what the other, what else we get when we take the, now let's see what we get when we take the fractional derivative of 1 with respect to the Riemann-Liouville derivative. So this is going to be d by dt of j to the 1 minus q of 1, evaluate t. So this is d by dt of, now let's go ahead and do it, it's going to be 1 over gamma of 1 minus q times the integral from 0 to t of t minus tau to the minus q d tau. Okay, not too bad. So now I can go ahead and just integrate that. So this is going to give me d by dt of 1 over gamma of 1 minus q of t minus tau to the minus q plus 1 divided by minus q plus 1 evaluated at 0 and t. And this is going to be the d by dt of 1 over gamma of 1 minus q times, now let's see, when I put in t, I get 0, and so that goes away. So then I'm going to end up subtracting what I get when I put in 0. So I get 0 minus tau, so let's say 1 minus q divided by 1 minus q. And so, oh, sorry, my mistake. It wasn't t that was being replaced, it is tau. So that should be t minus 0 times the minus q, 1 minus q. T minus 0 is raised to 1 minus q divided by 1 minus q. And now let's see what we get. So we get d by dt of 1 over gamma of 1 minus q times, say, t to the 1 minus q divided by q minus 1. Okay? Is that what I really want to write? Did I do everything okay? Let me see. Oh, you know what I missed? Back here with the chain rule, we're integrating with respect to tau, so I should have popped out a minus sign. So this should have popped out a negative 1 here, right? And then that would have canceled the other negative 1, and I could leave that here as 1 minus q. I apologize for that mistake. Okay, so. Okay, finally we're at a point where we can take the derivative of this thing on the inside. And so popping out of here, we have 1 over gamma of 1 minus q times 1 minus q, which we can simplify later. And now we're going to take the derivative of this guy, and that's going to leave, say, a 1 minus q times t to the minus q. And so that leaves me with 1 over 1 gamma of 1 minus q, because this and this cancel, and times 1 over t to the q. All right, so all that work basically showed that the Riemann-Liouville derivative, so Riemann-Liouville derivative of 1 is not 0, and the Caputo derivative of 1 is 0. So these are definitely different operators, and it's more than just what we were saying back here with the two Laplace transforms. They act on constants completely different, and so that means they're going to act on a lot of other things differently. In any case, so that's a big crash course on fractional derivatives, what they are, and two of the big principal ones, where you have the Caputo derivative and the Riemann-Liouville derivative, and they both end up giving you different operators, even though they're really just an exchange of the two same operators, just done in different orders. So, in any case, I hope you enjoyed it. I apologize for any mumbling or any mistakes, and yeah.
Hey, recording? Yeah, it's recording. Hey, welcome back. So, that is fractional derivatives. So this is the Caputo fractional derivatives, the one that I really like to work with myself because of the integer order features that has for initial value problems. A lot of my work that is related to this, it comes through numerical methods for these sort of problems. I don't do so many direct applications, but I do have a few Hilbert space ideas that connect back to fractional differential equations. So, for instance, I have this paper called the Mittag-Leffler space of entire functions, and that's a neat way of connecting fractional differentiation to Hilbert space theory, which generalizes some work that's been done in quantum mechanics, and then I have some future work which I'm not going to talk about yet, but hopefully I'll put it on the channel. But yeah, mostly I've been concerned with numerical methods and helping people find ways of analyzing these systems that other people haven't worked on. Yeah, so this is all fun, and yeah, I hope you enjoyed it. Okay, bye-bye.